Okay, welcome to the third lecture of geographic applications of remote sensing. In this lecture, I'm planning to discuss some topics, theories, terms, and techniques in aerial photography. Okay, um, the content of this lecture cannot be found in your in your required texts. Let me get to the syllabus of this course, okay? So the required textbook for this course is Introductory Digital Image Processing, okay? A remote sensing perspective. But for this lecture, okay, the content of this lecture can be found in this optional reference, Remote Sensing of the Environment, an Earth Resource Perspective, okay? If you do not have this book, it's okay. The knowledge here contained in the lecture is good enough to meet the requirement of this class and the exam, okay? So if you have the book, good. If you don't have it, it's okay. As long as you finish this lecture, you will be good enough, okay? Okay, let's get back here. So there are four parts in this lecture. I'm going to use three video clips to finish this lecture. The first video will include vantage points and also aerial cameras. And the second video will be about aerial photography filtration. We're going to talk about different color theories and how to apply them to make filters for aerial cameras. The last video clip will be about aerial photography films. We're going to talk about how to properly use different types of films to acquire images. And you can say that all this lecture is based on analog imaging systems, okay, because we're going to talk about cameras, filtration, and the films, and we don't use films on digital cameras or digital sensors today. You may say it's old-fashioned. Yes, it's old-fashioned. It's old school stuff, but it doesn't hurt to know them. And actually, it's very necessary for you to know how old-fashioned analog cameras work. Okay. Okay, let's get started. So the first term I want to introduce in this lecture is called vantage point. Okay, specifically, the first part of vantage point, first type of vantage point I want to introduce here is called vertical vantage point. Okay, here is a figure giving you an impression of vantage point. So here is a plane carrying a camera, right? So camera is looking at the surface of the Earth. And at a specific time, the camera is looking at this area on the ground defined by these two dashed lines, right? So these two dashed lines is a current FOA, It is indicating that this area defined by these two dashed lines, okay? Okay, this area is the area covered by the camera right now. And for each camera, there is always something called an optical axis. And the intersection between this axis and the ground is what? This intersection point is PP, principal point, Camera's optical axis is within 3 degrees of being vertical to the Earth's level surface. Okay, so principal point here is also considered as the vantage point. And how about this solid black triangle? This is the area that this camera can observe. Because usually a camera, when the camera is looking at the surface of the Earth, it can also rotate to the left, to the right, but there is always a limitation in terms of the angle that this camera can rotate. Okay, so this triangle here, especially these two solid lines here, they are the boundaries of the camera, because you cannot rotate to a very large angle. Okay, so here our vertical vantage point, when the plane is flying over right above a specific area, and the camera is looking at the surface of the Earth right below the plane. This is the situation, right? So this is the principal point. This is the principal point of the camera, and this is the whole area covered by this camera right now. And you should know that there is no distortion at this principal point or vantage point. Because this camera is not very high compared to satellites, cameras on satellites, but there is still distortion when the object is away from the principal point. The distortion is very small, okay, can be ignored, but you should know that principal point is where there is no distortion. Okay, on the right side we have another example showing you vertical vantage point. There is no reference lines for this photo, but it's somewhere in the center. Okay, and you can see that both these photos, they were taken when the plane was right above this area. So camera was looking down vertically. And we can also define oblique vantage point. Okay, the camera's optical axis deviates more than 3 degrees from vertical. This is the situation here. Okay, again, the plane is flying towards you, but the camera is not looking at the ground right below the plane. It is looking aside, looking away from the area right below the plane. Okay, it is looking away. So still there is this optical axis, and the intersection between this axis and the ground is also the vantage point, but this time it's not vertical vantage point, it's oblique vantage point. And there are two scenarios or two situations for oblique vantage point. And here we are looking at the scenario or the situation called low oblique, because in this photo, okay, here the solid lines, 3 solid black lines, they are addressing the area, right, covered by the camera right now. And within this area, horizon cannot be seen. For example, this. Okay, so obviously this is a bridge, road, with road, of course, with road. And this picture was taken using an oblique direction. So you can imagine that the plane is flying from this way, and the camera is looking away to take this photo, of the bridge. And the vantage point is somewhere here on the bridge or in the river. It doesn't matter. But what matters here is that you cannot see the horizon in this photo. So it's low oblique scenario. Okay, so since there is low oblique scenario, there is also high oblique scenario in which horizon is visible. So here you can say the camera is looking away. Is similar to the low oblique situation, but here the camera also includes the landscape very far away. Okay, which means that here you can say that this is a horizon Horizon is the boundary between sky and the ground, right? When you're looking very far away. Obviously, um, um, the main character of this photo is this bridge and this dam. I would say this dam is the main character, right? And we also have mountains and rivers, but since this plane is very far away from the dam, in order to put this dam into this photo, into this image, you have to rotate for a very large angle to make sure that this dam is within your frame. And the result is that horizon has been included in this photo. And so for this scenario, your oblique vantage point could be very far away from the center of the photo, could be somewhere here on the dam, or even further away, somewhere within this mountainous area. Okay, but I mean, the concept of vantage point is not that complex. It's just the intersection between the optical axis of a camera and the ground But we have different scenarios. You need to be clear with that, and you don't have to say memorize everything, but you just need to have this concept in your mind. Okay. Okay. So next, I want to talk about the structure and different types of aerial cameras. Okay, so in general, the structure of an aerial camera is very similar to our eye system. Okay, so here is our human eye system. When we're looking at a tree, the image of this tree will be projected onto the retina of our eye, right? Through what? Through lens, through iris, right? Through iris, and you can adjust the opening of iris to adjust the amount of light that can go through our eye. It's similar. It's similar for a camera here. So here is a tray. A camera also has a lens system, and it has something called aperture. An aperture can be very huge, can be very small. It's just like iris. It can be adjusted to make sure that there is a control of amount of light that can go through the lens system. And there is also a concept called focal length. It's the distance between the center of lens system and the film plane. And the film here is just like retina, is where the object is projected on. Okay, so this, of course, there are more. If we go in details, a camera can be very complex. The optical system inside, different types of lens, different types of aperture, different types of films. It can be a lot, but the general structure is just like this. Okay. Okay. And the next concept, next term you should know about aerial camera is called nodal point. Okay, a nodal point is where light entering the lens converges into a point and then diverges to impact on the recording medium. So on the right side, again, we have another figure to show you the structure of a camera, and here we have two nodal points. So here we have this lens system, right? And specifically, there are actually two lenses. Here is a rear lens. Here is a what? Front lens. So there are two nodal points. Okay, the first nodal point is where light entering the lens converges into a point. Okay, and there is another nodal point, it's called lens rear nodal point. Here is where the light diverges to impact on the recording medium. Who's the recording medium here? It's the film. It's the film. Okay, And the focal length, again, is the distance from the film to the lens system, And here, before the lens system, there is a filter here, okay? In the third part of this lecture, we're going to talk about different types of filters and say what they can do, why they're necessary, okay? Okay, next parameter I want to introduce here is pretty important, is called f number. Sometimes some people call it f stop or f rating, but you should know f number, f stop, f rating, they are actually the same thing. So it is a ratio, It is the ratio of the camera lens focal length. Okay, we discussed about this. F is the distance between the film and the lens system. Okay, it is the ratio of f to the diameter of the lens opening, which is d. Okay, let me get back here. So actually, here there is no shutter aperture here. Let's use this figure to show you. Like I said before, the aperture can be controlled. It can allow a lot of light to go inside the camera, or it can be very small. The diameter could be very small. So there is only a small circle that allows the light to go in the camera. So the size of aperture can be adjusted through what? Through changing the diameter of aperture. That diameter is what? Is D, lens opening. So F number is the ratio between F and D. Okay, usually we change D to adjust F number. Okay, of course you can change F, but it's more convenient to simply change D. So because D is on the denominator of this ratio, so the larger the D value, the smaller the F number. The smaller the D value, the larger the F number. Okay, D and F, they are inversely proportional to each other. Okay, F number is often used to designate the relative aperture setting or speed of the camera lens system. The smaller the f number, the greater light admitted, the faster the lens system. It makes sense, right? The smaller the f number, the larger the d value, the larger the lens opening. It makes sense. The larger the opening, the greater light admitted, right? Okay, here is an example. A camera with a focal length of 100 millimeter and a lens diameter opening of 10 millimeter. So what's the f number? Okay, so here f is 100, d is 10. So the ratio should be what? Should be 10. Okay, it's just that easy. So here I'm providing this figure to show you, to give you some impression about the relationship between the size of aperture and f value. So here, we can say here we have a huge aperture here, right? This white area is the opening of lens. So because it is very huge, so actually the f value is pretty small, because f value and the d value, they are what? Inversely proportional to each other. So the larger the aperture, the larger the d value, the smaller the f value. Okay, so as the f value increases from 2.8 to 4 to 5.6 to 8, you can see the aperture decreases continuously. Of course, you can make it even smaller to f value of 11, 16, or 22. Aperture here at 22 is very small. You say, how can I decide the aperture? Sometimes you have to try. You have to try different settings, and you need to use your experience. And it also depends on the weather, the environment, okay, the direction of your camera. Sometimes when the weather is pretty bad, you want to actually allow more light to go in, because it's cloudy already, right? If you want to take a very clear picture, you want more light to come in. So you may want to use a very small f value to make sure that the aperture is very large, so you can admit as much light as possible, right? That's just one example. If you are a very experienced photographer, you know what I'm talking about. I'm a amateur, so this is all I know. But the concept here is f number. It's a ratio between f and d. Okay, that's all you need to know. Next parameter I want to talk about here is called shutter speed. Okay, shutter speed is also called exposure time. Exposure of who? Exposure of the film in your camera. So the length of time that the shutter is open, that is shutter speed. It could be 1 second, it could be 0.75 second, it could be 0.01, which is 1/100th seconds. Okay, the longer the longer the time, the longer the exposure of the film, the more light energy can go in your camera. Okay, so usually the shutter is closed to make sure that the film is not exposed to what you don't want to take for your picture. When your camera is looking at something you're interested in, you open the shutter for a specific time so the film can capture what you want to say, and then you just immediately close the shutter again to make sure, okay, I have captured what I want to say on my film, and now I need to stop the exposure of the film and close the shutter. Okay, so usually, for example, here, an ideal aerial photography exposure at 1 p.m. in the afternoon in clear sunlight is with a f number of 16 and what? 1/200 second as shutter speed. Okay. Okay. So if we're taking a picture in a cloudy day, the light is not that good. To obtain a well-exposed picture, we should use smaller or larger f number and a faster or slower shutter speed. Okay, we should use a smaller f number because again, f number and the diameter of aperture, they are inversely proportional, right? So if the f number is small, the d value, the diameter of the aperture should be large, right? That's what we want, like I said, because the weather is bad, the light is not enough. So you want to make sure that aperture is large enough to admit more light. So bad weather, smaller f number, which means larger d value, more light. And another way to increase the amount of light is what? Is to use slower shutter speed, which means that the shutter should be open for longer time, so more light can be admitted. Okay, here is just a very simple example to give you the impression, the importance of f number and shutter speed. In a specific real mission of aerial camera, when you want to shoot something, or you're a professional photographer, of course there are even more factors you need to consider. But just when we're ignoring all other factors, now you know how to adjust f number and shutter speed to make sure that you have enough light energy, okay, projected on your film, of course. Okay, that's shutter speed. So in the last part of this video, I want to give you some information about different types of aerial cameras. Okay, the first type is very simple. It's called single lines mapping or metric camera. It can map the planimetric location of features and derive topographic or contour maps. It can provide the highest geometric and radiometric quality aerial photography. Okay, so here we have seen this structure figure for this camera in previous slides, right? So this is a structure. On the left side, we have a picture of it. You can see it's very old. It's very old. It's a product before the era of digital image. Okay, and here is an example of its product. So here is a picture took by that single lens camera. And this picture is actually very complex. Of course, we have the area we're interested in, but there are small features around this picture we should know what they are. So number one here, we have different small circles with different grayscales. They are actually serving as the legend of this picture, just like a legend for a map. It's grayscale step wedge. So different grayscales, they are addressed here. So it's easy for the reader to compare this legend with the map. Not the map here, it's with the image, with the photo. So number two here, we have an empty notepad. You can write something on it. Okay. Number three, altimeter is elevation of the camera when the photo was taken. Number four is called fiducial marks. Number four, fiducial mark. Another fiducial mark. The third fiducial mark. There is another one at the bottom of this photo. You can imagine that because obviously they are serving as anchors. Okay, they're serving as anchors. Number five is the clock. It shows the time the photo was taken. Okay, number six, lens colon serial. Here is the serial number of the lens of the camera used to take this photo. Okay, so it's the ID of the lens in the camera. Number seven, focal length. 153.34. I think the unit here is what? Is millimeter. Cannot be centimeter, right? A focal length of more than 1 meter, that is not possible. So I think it's millimeter. Okay. Number eight, flight number and frame number. It's about this mission. Okay. Each flight can be a mission. A mission contains multiple flights. Okay, this is flight 30, and this is the number 18 picture of flight 30. Okay, that's number 8. Number 9, mission ID. Mission ID. What's this? Mineral Wells 2, November 1989. Okay, so that's the name of the mission. Of course, you can also add the date of the mission to the photo. Okay, of course, if you want to add some information here, you need to, do some configuration on this camera. You can say it's old-fashioned. It's old-fashioned. We don't have this type of camera in our department. Maybe we have. Okay, if I can find some, I can show you in the classroom, but not in this online class. Okay. So since we have single lens camera, we have multiple lens camera. So here is an example. You can see actually it's 4 cameras. They are combined. They are mounted on this device, to make sure that at a specific time they're looking at the same area. Why do we need multiple lens? Because each one can be responsible for a specific band. Okay, for a specific range of wavelengths. For example, we have 4 photos taken at a specific time, and camera 1 is for the imaging within near infrared band. Another camera is responsible for the red band. The third camera is responsible for green band. Okay, 1, 2, 3, 4, right? Four cameras. The last one, I suppose, is for blue band, but the information is covered here. Okay, so for near infrared band, this image, I mean, the value of each pixel here is what? Is actually the reflectance of that pixel within near infrared band. Okay, so you can consider multiple lens or multiple band camera as a combination of multiple single lens camera, each one for a specific band. Okay, and we can also use something called panoramic camera to cover an even larger area. No matter a single lens or multiple lens camera, they cannot rotate themselves. If they want to rotate themselves, I mean, the whole airplane needs to rotate. Because there is no rotating structure on these cameras. But I don't have a picture here, but here is a description for panoramic camera. Use a rotating lens to produce a narrow strip of imagery perpendicular to the flight line. This is very similar to the whisk broom detector I introduced in the last lecture, right? The sensor, the aircraft is moving along a direction, say from east to west. But this camera mounted on the airplane, it is looking at the ground and it is rotating from north to south, which is perpendicular to the movement direction of the aircraft. So it will produce narrow strips of imagery perpendicular to the flight line. Okay, if you cannot remember, you should go back to lecture 2 and find that slide showing you the structure of a whisk broom detector. Okay, and we also have digital camera. Obviously, this is the main character today. I mean, we're in an era of digital camera. Okay, uses an area array of solid state charge coupled device. It's called an area array of CCD detectors to record information, optical information. Okay, on the right side we have a Kodak DCS 420 digital camera with a Nikon camera lens and body. So again, even this is a digital camera, it looks old. Today, when we are carrying out a remote sensing mission, of course, you can still use a camera. But today, usually we use more advanced remote sensors. You can consider sensors, they are special cameras, but they do not have this very typical camera shape and structure. Okay, that's all you need to know. Okay, I will just stop here. From next video. Actually, the whole next video will be about aerial photography filtration. We're going to discuss different two types of color theories and how to use them to produce filters. And you will also know why we need filters. Okay, thank you.